Each year, as the air grows crisp in New England, a familiar rhythm begins anew. From across the campus they arrive, some curious, some experienced, all drawn by a singular idea: to build something that will rise. They are not animals preparing for winter, nor machines executing orders. These are students, engineers, coders, machinists, scientists, gathering in basements and labs, united by a dream older than humanity itself, the dream of flight. This is HPRC, the High Power Rocketry Club, and this is their story. In the pages that follow, we shall observe their world, not from afar, but within. We shall watch their hands as they shape fiberglass and aluminum, as they test circuitry and hand-sewn dishes. We shall listen not to bird song or rainfall, but to the hum of motors, the whine of belt sanders, and the murmur of minds in motion. Over the course of the next 40 minutes, we will explore the three domains of their endeavor. The rocket, sleek and powerful, carrying with it their finest mechanical work. The payload, a delicate machine known as Persephone, which must land, drill, and plant new life in the desert. And ENP, electronics and programming, the neural web that brings logic, vision, and voice to the rocket and payload itself. It begins not with ignition nor flight, but here, in these early meetings, where strangers become teammates, where pasta towers stand in for aerospace composites, where chaos begins to take form. They do not know it yet, but before this journey ends, they will build something few have ever built. They will cross mountains and deserts, and they will launch their creation into the sky. This is not a story of perfection, nor one of ease. This is a story of resilience, collaboration, and the ancient pull of gravity overcome. And in that struggle between what flies and what fails lies the weight of Elysium. Our journey begins with composites, the team responsible for crafting the fins and outer structure of the rocket. These surfaces must endure the heat, speed, and turbulence of flight without bending, burning, or breaking. But before they begin working with epoxy and fiberglass, their first challenge is something far less technical and far more telling. Let us step back and observe. This is the composites interest meeting. But today, there are no molds, no measurements, just dry spaghetti, Swedish fish, and a pizza timer. Their task? Build the tallest tower they can.
Interview time, what's your plan?
Pyramid. Yep, pyramid.
Pyramid?
Yep.
All right. Sounds good.
Triangles are the strongest shape.
Figure it out as we go.
All right.
Won't work out well.
Cool.
Got big plans.
Big plan?
It's like this shape for our size.
So we're gonna make a square.
Okay.
We're just gonna put a strip.
All right. Sounds good. Yes. Plan? Plan. All right. Sounds good.
It is chaos. Pasta snaps, fish get eaten, and towers collapse in slow motion. But through the laughter, something forms. Not just structures, but a sense of cooperation. Ideas are exchanged, voices overlap, and beneath it all, the earliest signs of a team begin to take shape. Now we move forward. The real work begins. Designs become patterns. Sheets of fiberglass are water jet cut, rough outlines transformed into precise fin profiles, sharp, identical, and ready for reinforcement. Layer by layer, fiberglass is laid down, wetted with resin, and carefully aligned. There is no rushing here. Each piece must bond correctly. Each cure must be perfect. What emerges is not just rigid, it's reliable. A structure designed to cut through the sky and bring the vehicle home again. And beneath the surface, held in resin and weave, is the memory of where it all started, with towers of pasta, and the first lessons in how to build something together. As the rocket climbs, it must one day fall, and when it does, it must survive. This responsibility falls to the recovery team, caretakers of descent. While others focus on thrust and trajectory, recovery looks toward the end. They are the planners of return, the quiet engineers of safety. Their tools are not forged in the machine shop. They arrive in packaging, parachutes, shock cords, hardware, ready for flight, but far from complete. For in recovery, it is not what you build, but how you prepare. A parachute is only as good as the hands that pack it. We now watch as those hands move with practiced care. Folds are made with precision, cords are coiled deliberately, and every movement is performed exactly as it must be.
In some cases, you don't roll, you fold.
The altimeters, small, silent, and essential, are tested over and over. They must listen for apogee, then speak with certainty. A burst of current, a signal to fire the charges. A delay of even a second could mean failure. So they rehearse, again and again. LEDs flash, buzzers chirp. Success is quiet but unmistakable. If everything works as intended, the descent is calm, predictable, slow. And this year, recovery did everything right. But as we will see later, not all outcomes lie in their hands. Some parts of the rocket are passengers, fixed in place, their role complete the moment launch begins. But mechanisms builds what comes alive in flight. Their most intricate creation, the air brake system. Tucked seamlessly into the body of the rocket are 4 slender panels. They do not hinge. Instead, they ride along linear sliders, recessed flush, until the moment they're called upon. They are powered by a single servo. At just the right moment, after motor burnout, but long before descent, the servo turns, rotating a central actuation plate. That plate, with quiet force, drives all 4 panels outward in perfect symmetry. The goal is precision. With no thrust remaining, the only way to shape the trajectory is through drag. The air brakes deploy not to slow the rocket arbitrarily, but to place it exactly at apogee, the highest point of its flight, before descent begins. Let us now observe as they bring these pieces to life, shaping raw aluminum into precision components, one cut at a time.
We're just going to kind of make the machine move.
The mill spins, coolant flows, chips scatter across the table. Piece by piece, the actuation plate, mounting brackets, sliders, and panel guides are carved into existence. In this work, there is no glamour, only focus, measurement, patience. Alongside the air brakes, mechanisms also builds the avionics bay. The chamber that houses the flight computers, power systems, and communication links that allow the rocket to think. Every part must be compact, durable, and secure. The brain of the vehicle must survive both launch and landing, but it is the air brakes that represent mechanisms at its boldest, a system of movement, decision, and control. For just a few seconds, high in the sky, the rocket listens, and mechanisms tells it where to go. Every organism needs a skeleton, a frame to hold everything in place. a structure to bear the load. For this rocket, that burden falls to the structures team. Their task is simple in theory: hold everything together. But in practice, it is anything but. From the instant of ignition, the rocket experiences forces that most machines will never know: vibration, torque, drag, bending, shock. A vehicle that cannot handle these loads will not complete its journey. So the structures team begins with the most critical components: the couplings. Rings of aluminum, cut from solid stock, are carefully machined to match the rocket's airframe. The lathe hums, calipers click, shavings curl away with every pass. These parts must connect major segments of the rocket, and they must not move, not by a millimeter. After machining comes preparation: tapping holes, deburring edges, labeling parts for assembly. And then comes inspection. Let us pause here to observe.
What we're going to do is we're going to get the plane.
I thought the camera was out of view by then, but
Do like a couple more.
Each coupling is measured, every surface examined, edges checked for imperfections, threads tested with bolts. If there is even a hint of misalignment, the part is set aside or reworked. No shortcut is allowed. Only once a part passes inspection does it proceed to the next phase: gluing. This is the first form of integration, setting the couplings into the airframe itself. Epoxy is applied. The parts are slid into place, clamped, and left to cure. There is no fanfare, no drama, just hands, resin, and patience. Here, the team is careful, focused, thoughtful. Every plate, every coupling, every screw serves a purpose. And yet, the forces of flight are cruel. Despite the hours of planning, machining, and care, it was ultimately the structure that gave way. But that is not this moment. This moment is about intention, discipline, craft, and the belief, held tightly, that what they are building is strong enough to fly. With the rocket now taking shape, its fins cured, its systems assembled, its structure reinforced, attention begins to shift, not upward, but downward. For while one team engineers the climb, another prepares for what happens after. This is Payload. Their mission is not about reaching the sky, but returning to the Earth and leaving something behind. The payload for this year is called Persephone, a small experimental system designed to deploy from the rocket at 800 feet, land independently, and plant a seed in the soil. A quiet gesture, symbolic, intentional. But to accomplish that, Persephone must survive its own journey, a flight, a fall, and a perfect landing. And so, just as the rocket needs a backbone, the payload needs one too. We begin with payload structures. Persephone is not meant to fly for long, but it must survive the fall and know how to land. Unlike the rocket, it will not stand tall. It stays horizontal even after impact, but orientation still matters. So the team designed a self-righting system, a set of 4 flat 3D printed paddles that extend outward and shift its weight. With a belt-driven actuation system, the paddles gently flip Persephone onto its correct side, ensuring it faces the right direction when it touches down, preparing for what comes next. With Persephone's structure complete, attention turns to its first task upon landing: preparing the soil. The ground prep team is responsible for drilling, creating a small cavity where the seed and water can be delivered. But this is not laboratory soil. It's the Midland Desert, dry, compact, and unpredictable. So the team designs a custom auger, small, light, and simple enough to be carried by the payload. It must begin spinning on impact and dig just deep enough for the seed to rest beneath the surface. Prototypes are tested, dirt is hauled in, the system is refined. And with each turn of the blade, Persephone becomes more than a passenger. It becomes an agent of change, carving space in the earth for something new to take root. With the hole now drilled, Persephone's purpose reaches its final step: delivery. Inside the payload, a seed rests behind a sliding door. When the system activates, the door retracts, and the seed falls gently into place, settling into the hole carved only moments before. But life needs more than placement. It needs water. To provide it, the team engineered a network of narrow hoses, each connected to a syringe. The syringes are compressed in sequence, pushing out a precise amount of water directly into the soil. There are no pumps, just timing, pressure, and intention. The system is quiet. It will last only seconds. But in that brief moment, Persephone completes its mission, not by collecting data or transmitting images, but by leaving something behind. With the seed delivered and the soil watered, Persephone's mission would have been complete. But none of it could have happened without the landing. Payload recovery was designed to make that possible. At 800 feet above the desert, Persephone would separate from the rocket, beginning its own descent back to Earth. A small parachute would deploy, slowing its fall just enough to protect the payload on impact. There was no backup, no second attempt. So the team focused on what mattered most, ensuring that the parachute would inflate reliably, quickly, and at the exact right time. Deployment was everything. And though the system was never tested in a full drop, its design was simple, proven, and built for that single moment. Because everything Persephone was meant to do depended first on making it safely home. With the rocket built and the payload prepared, one element still remains, unseen, untouched, but everywhere: ENP, electronics and programming. If rocket is the body and payload the hands, ENP is the mind. Here, there are no fins to sand, no parachutes to fold. The work lives in code, in circuits, in timing, and yet, without it, nothing moves, nothing speaks, nothing works. 3 teams share this space: software, simulations, and the ground station, each responsible not for building what flies, but for knowing how it flies. We begin with software. Divided between rocket and payload, the software team is responsible for writing the logic that guides every action the vehicle takes. The rocket branch programs the flight computers, monitoring altitude and controlling the air brakes with millisecond precision. Payload software builds a separate brain, managing states for separation, self-writing, drilling, and delivery. It is invisible work. But inside each board, each pin, each string of code, lies the quiet intelligence that makes this system more than just a machine. Alongside software, another quiet discipline supports the mission: simulations. Their models predict how the rocket will fly, how air brakes will affect altitude, how forces will shift in motion, and how systems will behave when theory meets reality. It is work done in silence, behind screens. But without it, there would be no confidence in the path ahead. Finally, we arrive at the most visible part of ENP, ground station. While the rocket climbs and the payload falls, ground station stays anchored, tracking, listening, and collecting every signal sent from above. Its centerpiece, a massive 2-meter-wide antenna dish designed and built entirely by the team. But before it could receive anything, it had to be sown. Let us pause here and watch.
Hello, Cameron.
Oh, hey, Cameron.
How's that going? We did interviews with some students. That's right. After I got up, walked towards the camera, and flipped it off as I was going past. Doing stuff like that,
This was not an off-the-shelf system. Every thread mattered. Every fold had a purpose. What followed was the rest of the assembly. Mounting, wiring, tuning, testing. A blend of mechanical precision and electronic complexity. When complete, the dish could track the rocket through the sky, down to just a few degrees of accuracy. Logging data, relaying signals, and keeping the entire flight within reach. It was a feat of engineering, a point of pride, and later, a point of recognition. With subsystems built and software in place, the time comes to test not just ideas, but actions. This is where theory meets practice, where simulations end and real forces begin. Testing. It begins with the ejection system. The charges that separate rocket sections must fire cleanly, releasing parachutes at precisely the right moment. A failure here could mean the difference between recovery and loss. So the team tests. The system is wired, armed, and triggered. Sections burst apart. The sound is sudden. The result, reassuring. And then, something bigger. First, dry run assembly. For the first time, major sections of the rocket are brought together, not in CAD, but in real space.
Right now it's hot blue. It's not inside. So what's actually going to happen?
We're gonna assemble things that came from the one mission.
Okay.
But specifically, you're in charge of those. Let's make it easier if we try to get air out. Okay, then now you're gonna do it.
A couple years ago, I will use it for HPRC now. So you can just leave it there.
I don't know where that is.
Just like something to grip on the tap into the voltage.
Couplings align, wires are routed, systems are stacked, adjusted, and inspected. The rocket doesn't fly yet, but it stands. And for the first time, it feels real. It begins with a journey. One car drove the entire distance, carrying tubes, tools, and precious cargo across 2,000 miles. The rest of the team flew in, touching down in Midland under cloudless skies. There were no labs, no workbenches, just luggage, rental vans, and desert heat. But this was it, the final stage. Every challenge they'd faced before was preparation for the ones that would come next. After arrival, the work began immediately. The first step at IREC, registration and safety review. Held inside the convention center, The review is where each team presents their rocket for inspection, not to launch, but to earn the chance.
Okay.
Sorry.
The rules are strict. The rocket must be fully assembled, complete, wired, and flight ready. Nothing can be missing. Nothing can be theoretical. Officials examine every part of the vehicle, checking for safety, stability, and system readiness. Questions are asked, panels are opened, recovery plans are reviewed in detail, and if something isn't right, they'll tell you. Launch approval isn't automatic. It must be earned. For this team, there was one issue, a small detail that needed correction. Nothing major, but enough to stop a launch if left unresolved. So they fixed it, quickly, cleanly, and just hours later they returned to the table, ready once again to prove they were prepared. This time they passed. The rocket was officially cleared to fly. The next day, the launch site opened. Teams rolled out their rockets, pads filled, engines roared, one by one vehicles took to the sky. But this team stayed behind. There were still loose ends, small problems, uncertain systems. The choice was not easy. Months of work had led to this moment, and they were cleared to fly. But something wasn't right. So instead of heading to the desert, they stayed at the motel. They opened the rocket again, adjusted, rewired, reseated components, reviewed every checklist twice. It wasn't dramatic, it wasn't loud, but it was the right call. Because flying isn't just about building something that can launch, it's about knowing when it's ready.
There's like two.
There are two multimeters in there. Yeah, there's well, I brought one down, but there's another one up there.
Have your card to grab it?
Yeah, it's on the table there.
This one?
Yeah.
You want to scrape it?
The night before launch, 5 team members stayed up through the dark, pushing through fatigue, trying to salvage what they could. 3 flight computers burned out in the process. One by one, systems failed. With dawn approaching, a decision had to be made. The payload board, never meant to control the rocket, would now serve as the primary flight computer. And the air brakes, once the pride of the design, would stay off. It wasn't the flight they had planned, but it was the one they had. And so, on launch day, they carried it to the desert floor. The morning was calm, the air still. A quiet tension settled over the site as teams moved deliberately, some with confidence, others with caution. For this team, everything now came down to this one moment. The rocket was unpacked, laid out in pieces. Assembly began, slow, focused, careful, not rushed, not improvised. Each bolt, each wire, each connection was made with the weight of everything that had come before. Let us pause here and watch.
That's good.
Now, the team drills holes for the shear pins, small fasteners that hold the rocket together in flight and break only when the ejection charges fire. And here, the final piece, the motor. Heavy, precise, powerful. With everything in place, the rocket is ready. And now they begin walking it out, toward the pad, toward the sky. At the pad, the rocket stood tall. Years of study, months of work, hundreds of hands, tools, tests and lines of code, now resting in silence under a desert sky. Final connections were made. There was nothing more to do. And so the team stepped back. From here on, it was the rocket's turn.
5, 4, 3, 2, 1.
Ignition. The rocket clears the rail, fast but unstable. It begins to spin rapidly, precessing around its center. Then, near burnout, the vehicle breaks apart. The epoxy joint fails. The rocket fractures mid-air. Parachutes deploy from the debris, but the flight is over. Not the ending they had worked for, but one they faced together. Now we look again in slow motion. Watch closely. The rocket begins to spin as it leaves the pad, and just before burnout, the structure gives way. Right here, the epoxy joint fails. The vehicle breaks apart mid-air. It happens fast, but not without reason. After the smoke cleared, there was only silence. But the team moved quickly. Debris was located, parachutes found. The airframe, split and scattered, was gathered piece by piece. One body tube had driven itself straight into the ground, wedged so deep it had to be dug out by hand. And yet, remarkably, every section above the failed coupling was intact, reflyable, still strong. It wasn't the recovery they had hoped for, but it was a reminder that not everything had failed. There was still something to hold on to, something to learn from, something worth building again. On the final day, the teams gathered one last time. The rocket was gone. The sky was quiet, but the work still spoke for itself. Among the awards given, one stood out. This team was honored with Best Live Telemetry Visualization, recognition for a system built not to fly, but to understand what was flying. The ground station team had built it from the ground up, coding a live interface from scratch and constructing the 2-meter-wide tracking dish that made it possible. And now, in a room full of applause, that effort was seen. It wasn't the ending they had envisioned, but it was one they had earned. The desert is quiet again. The rocket is gone, but its story remains, in data, in fragments, in memory. More importantly, in the team that built it. They came here to launch a rocket. What they left with was something more. Experience, understanding, resilience. They learned what holds a rocket together and what doesn't. Now, the next chapter begins. Next year, the team will build 2 rockets. One, a 2-stage test vehicle designed to explore staging, ignition, and mid-flight separation. The other, a 30,000-foot single-stage rocket built for competition. The challenge is greater, the altitude is higher, but so is the team's readiness. Payload will move toward mobility, designing a new rover platform to deploy and explore on its own. The vision expands beyond planting. ENP will continue pushing the boundaries of flight software and telemetry, building smarter systems and clearer connections between ground and sky. Rocket Division will tackle staging, flight reliability, and high-power propulsion, all while preparing a vehicle to reach nearly 6 miles above the Earth. 2 rockets, 1 year, driven by everything they've learned and everything still ahead. Because the weight of Elysium was never just structural, it was the weight of purpose. The weight of flight. The weight of knowing that next time, they'll be ready. The Weight of Elysium. A film by the High Power Rocketry Club.